All right, so hi everyone. Welcome to the Growth Index School. This is the second lecture on higher algebra theory on Quillen's plus and Q construction for K theory. And once again, the speaker is Professor Girja Shanker from MISA Tirupati. Yeah, over to you, Professor.
Okay, sir. Just a minute. So we'll start then. Yeah, so last time somebody had asked this question about, so I'll correct it and then we continue. Okay. So they had asked this question about one missing code-face map. Yeah. So that's actually always there. So can you say it properly, or some letters are being cut? Oh,
yes, better now. We can see the screen. Okay.
Yeah, so here, if you, so yeah, somebody had said that it should be n, and that's true. Yeah, somehow I made a mistake in my notes, and I'll goof it up if I start to correct it now. Yeah. So the last one, if you remove the last one, then what we really get is actually just inclusion, actual inclusion. Yeah, but it's there. Okay, so I'll continue writing on this. Yeah, so last time we described this classifying space of a group. Yeah, and today now we will describe our topological space BGLR plus and define K groups as its homotopy groups. Yeah. Okay, so how did it go?
Sir, I have a question from the last lecture.
Okay.
So can you please go to the portion when you have defined the nerve and the nth piece n minus 1 is 1th piece?
Okay. Let's see, somewhere here. Maybe.
Yeah, here.
Oh, okay, yeah.
So here you have defined the DI maps that it is some composition of n minus, I mean,
any
n
two
maps
adjacent
to n.
ones. Yeah.
Yeah. So here, do you have only n minus 1 many map, or we have two more extra maps, like omitting A0 and then another is omitting the last one?
I guess nothing is omitted. You just compose. See. So,
yeah. You composed A0, A1, and A2, and then you wrote A0 to A2, right?
Yeah. So this was example. This was just for n maybe 3 or something. Yeah.
Yeah. That is an example. I am asking that whether this is another example that A0 is omitted, and then A1, A2, A3.
No. So none of the objects are okay. So okay, I see. Oh, so actually objects are here. Okay, let's see. I have to try to remember now. So let's say, yeah. So D0, D1. Now if I want to look at D3, then what do we combine? So yeah, okay, let's have a look at this also. I have to remember, yeah.
Can we take, because this is only a string of composition, so can we take A0, A1, and A2 and that's all? I mean, can we ignore A3?
So in this case, Okay, so let's see. So we compose these two, then we got this. Now for D2, so what do we compose now here? So D0 we compose these two, D1 we compose these two. Now D2, what do we do? How do we? So for D2, okay, so for D2, how do we get? So we want to reduce it to, yeah, so we have to, yeah, leave some things out. Yeah, you are right. Yeah. So like here we ended up leaving that term out. That yeah.
Exactly.
So you have to adjust it in a way that you have to properly leave. Yeah, depending on, yeah. So for example here, so what do we leave this time?
I mean, do I have to fix my initial and final object, or it is allowed that the final object may change or the initial object may change?
So the point is we pick up the objects based on the images, yeah, and so the part that's left out, so see, yeah, the problem would be in the end, yeah, like dn will leave this out, the very, no, dn will, no, d0, so maybe I might have, so d0, what does d0 do? D0, so yeah, so thanks for pointing. I guess D0 is off here in some, so D0 will leave this one out, looks like, yeah. Yeah, okay. So, but others would work like compositions. So the end ones will, okay, thanks for pointing this. So end ones, D0 and the last one, you have to modify, but others, yeah, so then you end up leaving actually. Thanks, I wasn't careful that time. Yeah, so here there is a D3 also, yeah. So D3 will leave, yeah, it will leave A3. So there is no composition, you just leave A3 and it ends up giving you just this part. Yeah.
Yeah. Thank you. Thank you.
Oh, thanks. That's very good. Yeah, I've not given any basic course on this for a long time, so I keep forgetting these things. Yeah, so it will go to this. This will be from for D3, and then D0 again I have to be careful, yeah. So D0 would be, we leave, yes, so the compositions would be for D1 and D2. So okay, then I'll let you fix this, yeah, you can think about it and fix this. So we check one more time. So check exact form, okay. Yeah, the end ones actually do this thing, and in fact, yeah, so that's one another thing here I can tell. Yeah, so here again, so I picture two of them, and if you look at just this last D2, it will basically be just this one, which is like embedding this at the, see, how do we make this simplicity? You start with point, it's here, then this one, then we add these, and then we add more. So the last one will pick up just the one simplex that you already had, and then you added more to get two simplex and so on. Yeah. So this would be for D0, no, D2. Yeah, image of D2. Okay, so we continue now. So this time we wish to see our BGL R plus. So if you remember, so maybe I'll quickly try to give some motivation of why somebody would want to define it this way, but yeah, you can go through books. And here is another good reference that I didn't tell last time, which I would say better than Bible's book. So it's Srinivas algebraic K theory. That's a lot more detail for everybody to read. Yeah. So you can go through this for details. Yeah. So BGL R plus, it's a topological space with some properties, and then K theory is defined to be its homotopy groups. Yeah. So then pi I, this is KIR, and this is a connected space. So this actually doesn't do anything to 0. For that you just maybe put K0R in here. So take the space K0R times BGLR plus. So why somebody would define it like this? So for this, remember you have seen K0, K1, K2, and I'm sure you would have gone through basic details also as to how they relate together, and yeah, why somebody should define them that way. So here is a quick way to see some of them. So we have our group GLR, and then it has this normal subgroup. In fact, it's commutator. It's also, yeah, the subgroup given by elementary matrices, and so K1 R is just this quotient. ER, or which is equal to this commutator, and it's abelian. These groups are not abelian, but so this one is abelian. It's abelianization of this group. In a sense, it's largest abelian quotient that one can make out of GLR. Yeah. And so, yeah, so this is our K1 you would have seen, and then we define this K2 R as a kernel of this map. So let's see. So yeah, so we define this subgroup. So it's K2R would be kernel. So we have 0 to 1 if you want to write multiplicatively. So 0 to K2R, and we have seen this Steinberg group. I'm sure you would have seen this. To GLR, there is this map, and yeah, so there is this exact sequence here. Okay, and yeah, so here, so this is Steinberg group with generators, which basically you could see, I mean, you could take generators that you could think of as being coming from or standing for infinite elementary matrices. Yeah. So so this is kernel of this phi, and they show that it's actually a abelian group, so kernel of phi. So that's how you define K2, and yeah, and also it's in fact, yeah, you would have seen that it's center of, so this is an inclusion, and K2R is center of Steinberg group, kernel phi. Okay, and these groups, one could think after going through some group cohomology, then yeah, So which groups can be identified with certain group cohomologies? So do you remember which one is K1 as a group cohomology? Yeah, and which one is K2 as a group cohomology? So K1 is, by the way, did you do this way or not? Did you relate them with these group cohomologies? Yeah, have you seen this equality or isomorphism?
Yeah, we have seen it, but we don't know the proof.
Yeah, so proofs, actually most statements, maybe this one could still prove, but for proofs I think you have to sit down and read things. Yeah, I mean,
Yeah, I see.
yeah, almost none of the proofs are kind of, you know, a few line long proofs. Yeah, all of these small things. So good, so at least you've seen these things. So yeah, so these groups can be thought of as certain group cohomologies, uh, cohomology groups of groups with coefficients in, yeah, certain modules over those groups. Yeah, and okay, good, so that's one thing. And while Quillen was studying these things and other related things, then he noticed that so one could do the following to the topological space BGLR. Yeah, so this understanding of these two groups in terms of group cohomology Quillen to give the first definition of higher algebraic K theory of rings. First, which is plus construction. So what he did was this general construction from topology, and he lifted it up in this situation with BGLR. So here is a theorem by Quillen. It applies in more general situation, but maybe for sake of time I'll stick with our BGLR. So the actual theorem is, yes, for statement one can quickly do, so I'll do that. So let's say we have a path connected space okay, and suppose its fundamental group with this base has a perfect normal subgroup. Suppose that maybe n So for example, if you take X to be your BG LR and take identity as, so this is only one element as a one simplex in a way, so that you take a vertex and this point. So hedge pi1 is just GLR and its commutator is perfect normal subgroup in here. So this is the case in which we would be interested, but the result is true topologically in greater generality. So we have a perfect normal subgroup of pi1. Then the result is that one can modify this space to get the following. Yeah. So you could write it this way. Then there exists a, let's say, map of topological spaces. That means continuous map here into some space. That's what you could call X plus, and with some base point. So there exists a map with the following properties. So first thing is, there is an exact sequence. So it looks like we have our subgroup. So this is a subgroup in pi1 of XX, yeah? And basically pi1 X plus X plus through this F. Yeah. So it ends up mapping this into so mapping N into the, so in the kernel of pi1 F, so the induced map on pi1 through this F ends up killing the kernel, and actually it's surjective. Okay, so that means your pi1 X plus it's, yeah, it's isomorphic to this quotient of pi1 XX with by N. Yeah, so there is this exact sequence. This means this is space that we construct this way, starting with any perfect normal subgroup. So its pi1 would be just the quotient. And the second result is about, so this map actually being a homology isomorphism of all local systems. Yeah. So induces a homology isomorphism of all local systems. So I wouldn't write in detail, so you can read. So it induces isomorphism of from X to X plus for all local systems. So maybe I can write like this. H star X to take any, so it will go the other way. Yeah. So if you start with some local system, you can pull it back to X, and isomorphism would be like this homology isomorphism. Okay. So we have this homology isomorphism, and then third one is uniqueness of this space up to homotopy. So I'll just write it. Yeah. This x plus x plus x plus is unique up to homotopy. Okay. So its construction is little bit involved, but it's still quite basic. So you could go through this, but the idea is, so starting with some space, some pointed space, and some normal, perfect normal subgroup in there, you can find another space which is kind of unique up to homotopy, and homologically you are not changing it in a way, but its pi 1 becomes the quotient of the pi 1 by that normal subgroup. Yeah. Okay. So the, yeah, maybe remark or hint, whatever you wish to say. So this is obtained from, I mean, you can assume your X is a CW complex to begin with. If not, then you replace it by CW approximation. So we obtain X plus by attaching two cells corresponding to generators. Yeah, with generators. So two cells to kill all the generators in here. Yeah, all the elements in here. Yeah, so we obtain from this by attaching two cells to kill the subgroup. I mean, this is a general technique. In fact, given an element of fundamental group, you can kill it by attaching cells and get some space. You end up changing that space, but at least you know that one element of fundamental group is gone. Yeah. Yeah. So by attaching two cells to kill the subgroup N. Okay. And then whatever you get, you have to again modify a bit to maintain this homology isomorphism, and then uniqueness up to unique homotopy would be okay. Yeah, so that's the deal with this. So yeah, any questions? Okay, so this is, so yeah, so as a corollary here, or yeah, we have our BGLR plus. So here you have to tell which subgroup we are taking. Yeah, you have to tell which subgroup we are taking. To this normal subgroup commutator. Yeah. This one is our pi 1 of BGLR. Okay. So thus we have found a space whose pi 1 would be K1 of the ring. So take higher algebraic K theory space, or this algebraic K theory space. Of a ring. So this is connected. Yeah. So you have to modify it so that even pi 0 matches. Yeah. To be, give this discrete topology K0R and then BGL R plus. Yes, and define the higher algebraic K groups of the ring R as homotopy groups of this space. Since pi1, pi2, they don't depend on this, so might as well for other groups you just we take just this space. Yeah, we put this only to match the k0, the pi0, this space with k0 R. Okay. Do we have any questions? Okay, so this is our higher algebraic K theory space, and this is definition of higher algebraic K groups. And as I tried to tell, while in some way roughly very briefly sketched why one would do this. So they had studied group cohomology of various subgroups around this, defining K0, defining K1, K2, and yeah, so they found that with this, yeah. So this definition of all groups agrees with K0 agreed by the way you put it, K1 also it agreed by the way it is, and K2 there will be some work, so it agrees with these. Defined kind of bit by bit before. Yeah, maybe one at a time. Okay, good. So this way we get our K theory space and higher K theory of rings. So some basic properties are, for example, the relative K groups, long exact sequences, functoriality. Yeah, so let's do one of these at the moment. Functoriality is R to S. Let's say we are given a map of rings. Yeah, so this will induce GLR to GLS and everything BGLR to BGLS, and you run through the constructions. Yeah, so this induces maps KIR, KIS via maps and yeah, compositions are, so yeah, if we have R to S to T, then compositions would be okay. So that way there is this functoriality of the spaces as well as the groups. And then there is this relative K theory. So in fact one could define something in some generality than just some ring and a map onto quotient by some ideal. So there is slight generality in which you can one can do this. Yeah. So relative K groups and long exact sequences of these K groups. So let's say we have again R to S. This time I need to name it ring map, and we have this induced map of so all they are connected, path connected. So what we do, yeah, so maybe these are right and point, so something unique. Yeah. And then general theory of so that will look like let's say so maybe I would say k n plus 1 s, which would be homotopy n plus 1th homotopy group of this to kn of this homotopy fiber, whatever it is, and then these are induced maps from map of spaces kn kf to knr to kns, and then from here we get now kn minus 1 kf, and it continues till this point. Let's say k1 s to k0. So here I have to be, one should be a bit careful, but I'll leave those details to you. So we have this map, and we can also, yeah, we can put k0r here, k0s here, and choose a base point. And if we do this, then the place where this sequence will end will look like this: k0 kf, and from here we have, yeah, K0 R with K0 S. Okay. Yeah. So in a way, so we get by taking homotopy fiber of induced map on plus constructions, we get this long eject sequence of the K groups. Okay. And one point is here. Yeah, so one of the points here is that so these groups, they actually coincide with relative K groups that have been defined before. So it's maybe remarked. The relative groups defined here coincide with the relative K groups of the kind, the ones that we have been that have been defined. Yeah. So K groups K, whenever they're defined, are I for ideals. Okay. Okay, good. So with this we have something, at least one construction of K higher algebraic K theory. And now let's move on to Quillen's Q construction that gives another description of K theory. Okay. Now, do you have any questions so far?
So this KF is actually a ring?
KF is homotopy fiber. It's supposed to be a topological space.
Okay.
Okay, yeah. So thanks. I should. Oh yeah, I should write pi n somewhere here. Yeah, these are pi n's. Thanks. Yeah. Oh, good.
Okay.
Yeah, all these are pi's actually. So homotopy fiber. Yeah. Okay, good. So this was another goof up. Yeah, and here also. Okay, thanks. Yeah.
Okay. And this for RNS it is Kn, and for Kf it is a pi n. Okay. And pi n of Kf is defined to be that relative K group R comma I in case of.
Yeah, so this I guess this how many so this you must have defined all those K0, K1, K2.
Yeah, K0, K1, K2. Yeah.
Yeah, so this will agree here. Yeah.
Okay.
Yeah. Okay, so this gives one construction of hierarchy theory of rings through plus construction or yeah, applied to BGL R relative to this perfect normal subgroup given by the commutator. Yeah, and that was I don't remember, but so people try to get all the groups, and yeah, maybe all these groups being defined in this generality, this is the first construction, yeah, where you get for any commutative ring all K groups, non-negative K groups. Yeah. So the second construction is through Quillen's Q construction. So this is so Q construction for exact categories and their K theory. So exact categories, have you seen them? Many of these recent lectures?
Yes, we saw them earlier.
Okay, okay, then I don't have to do too much here. Yeah, and have you also seen this Q construction here in some form?
No, I don't remember.
Okay, that's
We
fine.
only
So,
saw the definition of exact categories, I think.
okay, okay. So exact category, I don't know in
Exact
what
categories,
general.
I think.
Huh? Yeah. Okay, so I'll quickly recall a form or just tell a few lines which is enough for us. Yeah. So for us, an exact category would be an additive category, which we take as embedded as a full additive subcategory in some abelian category and also as extension clause. So C. So for our purposes, this is what we will take, is an exact category if it can be embedded as a full subcategory into an abelian category let's say C to A. So embed, and also C has to be extension closed. In a way that C is extension closed. That means the following. So if we are given an exact sequence in A, yeah, that is given let's say 0 to m prime to m to this, an exact sequence in A where exactness is meaningful, with m prime and m prime prime objects isomorphic to objects in C, then this has to be isomorphic to an object in C. So And yeah, so with this, so in a way, exact categories for us would be full additive subcategories of abelian categories with just this property, and it allows one to consider what one would want to call monomorphisms or admissible monomorphisms and epimorphisms. Admissible, one would want to call admissible epimorphisms. I mean, that's how Quillen termed them. So yeah, in an exact category, yeah, so we have admissible monomorphisms and admissible epimorphisms. So admissible monomorphisms are the ones which can be completed as this map, first map, the kernel part of an exact sequence in the, yeah, and admissible epimorphisms in C are morphisms of this kind which can be completed into exact sequence like this. Basically, yeah, so we look at all the exact sequences here in C, and then yeah, so these will, oh, it's wrong spot. So these will look at here and these are modules, and we can think of it as and the exact there. Here from the same category to see given an exact category. An exact category, so Quillen constructed or defined Q, this category QC. So it has same objects as C, and a morphism between two objects is given by isomorphism class of the following data. Let's say x to y into c is isomorphism class of okay. This is an isomorphism class of yeah, this data. Pairs. It's not a good. Okay, so here pairs of morphisms in C. And y, and going wrong way, there is an admissible if we let's say exact category, we define its zeroth K group. Yeah, sorry, I forgot, I should have done it before. C exact category, we define its zeroth K group K0C as this quotient, where F is the free abelian group with generators objects of C, and this subgroup R is generated by these elements. Generated by, let's say, M. So yeah, M minus M prime minus M prime prime every time there is an exact sequence with M prime, M, and M double prime. Exact sequence in C. Okay. Yeah, so we have this K0 of an exact category. The definition is just a free abelian group generated by objects modulo this subgroup. having these relations. In a way, it's yeah. So it's to take the monoid here, isomorphism classes of objects and group completed. So, yeah. Yeah, so we have K0 of an exact category. We have Q construction of the category Q of an exact category. The next thing would be, so yeah, so composition in this category in QC. Yeah, so QC has objects of C. Morphisms are equivalent isomorphism classes of these two morphisms, the isomorphism described here. So we compose, so composition in QC is defined as follows. So write morphisms slightly differently this time. So let's say we are given X and Y and a morphism given by a diagram of this kind, morphisms this kind, this epimorphism and this monomorphism. So that will tell us some morphism in QC, yeah, isomorphism class of this. Yeah. And then let's say Y to W, we have another morphism. So this would mean that there is some object V and epimorphisms here, epimorphism here, and monomorphism here. Yeah. So it's one of the properties, depending on in whatever generality one works with exact categories, is one of the properties that every time we are given a pair of morphisms like this, push outs exist in that, no, pullbacks exist in that category. Yeah. So here pullbacks, so we take pullback of these two morphisms. So this would be, we could write so we have, so by definition, so this is part of data of exact category. Okay, so this exists together with these morphisms, and they are supposed to have this property that the one that we pull back along an monomorphism should be a monomorphism, admissible monomorphism. The one that we pull back along an admissible epimorphism should be an admissible epimorphism. So now also monomorphisms, composition of monomorphisms should be monomorphism, composition of epimorphism should be epimorphism. So now this is the way to compose. One checks that this is well defined. So this defines composition in QC, a pair of morphisms from this object to Q, which is admissible epimorphism, and morphism which is admissible monomorphism. So this is Quillen's category QC. So here is a theorem. It's actually, it needs some work. Yeah. So let you read it. So we have our category QC. We apply, so we can take its NURB and we can apply realization of it. We get a topological space. Yeah. So yeah. So what do we say? Okay, maybe I'll tell one thing and then say this. Okay, so this theorem I just write, yeah. So we have defined K0C as this group F modulo R, and the first theorem is that there is a natural isomorphism between these two. Pi 1 of we take nerve of QC and its realization. So just BQC. Let's say we take base point 0. Okay. So this is isomorphic to K0C. Yeah. So whatever has happened, so this was defined entirely in terms of C, and then we got this new category, which tried, at least there is a way to think of it as kind of group completion. And then, yeah, so for this topological space, nerve of QC, its pi 1 is just K0C. Yeah. So here now, so for example, so if we take C to be proj R, then now we are in this situation that we have K0 proj R, and so this is some group, and we have also seen K0R. So the next theorem is that actually these are isomorphic. Yeah. So apply Q construction to this category and take its pi 1 or take its K0 defined here, and that same as K0R. So yeah, so maybe this you would have seen anyway. This follows from basically definitions. So the actual theorem is here. You start with C, and yeah, so this you would have seen while defining K0R. Yeah. So this one is actually a serious theorem, that pi 1 BQC, this base point is just K0C. So actually here there is no example. This is just something the example will come next maybe. Yeah. This natural isomorphism, and this allows us to, after maybe some more thought, so this gives another definition of higher algebraic K theory. Yeah. At least for rings. So we have Ki, Ki. So we have this space, we take its homotopy groups. So I have to be a little bit careful here because with this index shifting. So K maybe I plus 1. Okay, so this definition. So take, so this is pi. Yeah, pi I plus 1. As pi I plus 1 BQC 0, and the next theorem is that this is isomorphic to this pi I, yeah, of BGL R plus 1. So BGL R plus. So phi I of BGL R plus. So yeah, this is again another theorem. So the theorem looks actually like this, and here yeah, I has to be at least one or more. So the theorem is like this. So there is a homotopy equivalence So homotopy equivalence would be like this. BGL R plus to, if you don't want to keep shifting this, then we change it like this. We take loop space of BQ PR. Yeah, so this C is PR. Q of P, so I'll call it PR. So BQ of PR. Take its loop space and take connected component of 0. So this is a significant theorem. Yeah, so maybe I should take one thing back. So this is actually, yeah, maybe not that significant. This one could sit down and try to work out. Yeah. But this one is significant theorem, that BGL R plus is homotopy equivalent to component here, this connected component. Connected component of, so here object would be 0, so you could take trivial loop based at, let's say, 0, and this is actually natural in maps of rings. Tutorial. Yeah, so this way now we have two definitions of higher algebraic K theory of rings.
Professor, we shall finish maybe within some couple of minutes.
Okay, sure. So yeah. So okay, so now we have two definitions of higher algebraic K theory of rings. I'll quickly try to recall one next time, or maybe not, but that's called S inverse S construction. But these two are enough for lots of properties. Anyway, the idea is that, so I would like to also at least one theorem, some steps I would like to sketch. Yeah, but the point is, most of these theorems, you have to sit down and go through their proofs in a way at your own peaceful place and time. Yeah, but still I'll try to explain some things. Yeah, at least one theorem, some steps. But yeah, as I said, all these proofs are fairly long. Yeah, so like, yeah, so we'll see how it goes. So here, yeah, so we have two descriptions of higher algebraic K theory of rings now. Okay, and here is a remark or definition. So yeah, this I'll finish with this. I'll call it remark and plus definition. So when we took this exact category of projective modules, finitely generated projective modules, and we applied Q construction and everything, then we got another description of K theory of rings. Now here, if we take, instead of PR, if we take this category MR, okay, so this is abelian. So sure, you can think of it as exact in trivial sort of way, the whole thing. Yeah. So we take MR. So also let's take R to be Noetherian. Yeah. These are any modules, finitely generated R modules. Edge and abelian, and hence an exact category. Then again we have, yeah, then we get, I would say, maybe K theory of this. MR, so means, yeah, we have MR, apply Q to it, take NURB, and okay, take loop space, again this phi I. So this is what we call G theory of ring R. So this is in a way K theory of finitely generated R modules, and so the G theory. Okay. So yeah, also called coherent K theory. This is K theory of finitely generated R modules. Yeah, so we have this, and we will see so how they relate whenever they relate. For example, so there is this inclusion PR into MR, and that should induce the maps of map from K theory to G theory. Yeah. So like when is that isomorphism? So these things maybe I'll quickly try to say next time. So maybe I'll stop here. So here you have another K theory for rings. So I'll stop here.
Okay. Are there any questions? Well, if not, then let's thank the speaker.
Thanks to you also for carefully pointing out little things. Yes.
All right. So we'll stop the session here then. We'll meet next week.
Okay, thanks.
Thanks for joining.
Okay, so I stopped.